So imagine that particle. We'll just start off with a ring. So imagine we have a metal ring. In that metal ring we have a current flowing around. A little bit like a solenoid, where we have a current flowing. And we can put our fingers in the direction that the current flows. And our thumb will point in the direction of north for this particular solenoid or coil. So we have a north here and a south in at the end or the other end. So that's a magnetic effect of a coil. Now when a current flows around a metal ring, it can be induced by a field, but we're just looking at a field produced by this particular current. And it flows around. If we put our fingers in the direction that the current flows, not a very good picture, our thumb will point in the direction of north. So in this particular case, we have the current flowing anti-clockwise, north will be up. If the current flowed clockwise, and we put our fingers around in that direction, then our thumb would point down. So this would be a north. Well, it's very similar for a particle in the nucleus. So if we think of a proton, sorry, I'll just correct that. If we think of a proton in the nucleus, the simplest atom is hydrogen. It has one proton and one nuclear particle. Now, in nuclear physics and things to do with nuclear physics, we often write these with the atomic number at the bottom, which is the number of protons. The top number will be the protons plus neutrons. And this number here is just protons. So hydrogen has one proton. If we look at it here, and it might be spinning in this direction, well, if we use that rule again, our right hand screw rule or grip rule, and we grasp that proton with our fingers heading around in the direction of spin, it will have a north vector or particle, or similar to a north pole facing down. If that proton is spinning in this direction, and we put our fingers around in this direction, the thumb will point up. And this is a right hand rule, so this would become a north. And if you think of that as a small magnet, each particle in the nucleus acts like a small magnet. Those that spin in this direction will have a north facing up. Those that spin in the opposite direction will have a north facing down. So we have these two possibilities. Now, in atoms with, say, like helium, has 2 protons and 4 nuclear particles. Remember, on the periodic table, helium is drawn like this. So we're drawing it upside down for our purposes. We do that in nuclear physics. So our helium has 2 particles, 1 and 2 in its nucleus. Sorry, it has 4, 2 neutrons and 2 protons. Here is the number of protons, so it only has 2. If we look at the number of protons, we have an upspin and a downspin, and we give upspins a value of 1/2. And we give downspins a value of -1/2. The total spin in terms of the protons is +1/2 plus -1/2, which equals 0. So when we have particles or atoms with even numbers of nuclear particles, 4 or the 2, we have a no net spin, 0 net spin. Particles tend to form pairs, and one spins up, one spins down. If we look at Another example, say lithium, 3 and 7. Remember, in the periodic table it's 3 Li 7 at the bottom, or 6.9. This means it has 3 protons and 4 neutrons, giving us a total of 7 nuclear particles. That's 4 plus 3 equals 7. So here we have 3 protons, and we would have one up, one down, and one up. Or one down, one up, one down. Doesn't really matter, but we have a net spin. If we give this value of a half, minus a half, sorry, this a half, this 1.5, we add them together, we get minus a half. In this case, a half minus a half, and a half, we'll get a value of a half. So we have a net spin, an overall spin. We have that with oddly numbers nuclear particles. Neutrons and protons can both contribute to spin. But overall, for a particle to have spin, it must have that odd number of nuclear particles. In this video, we're looking at the properties of particles in the nucleus. And one of those properties in particular is spin, nuclear spin. Protons and neutrons both have spin, as you can see here in the diagram. Depending on how they spin, there's a spin vector, and we're going to have a look at that right now. Normally in compounds here we have in the body, say, or just a collection of nuclear particles here. They spin in all different directions. You can see they're quite random, much like the particles in a non-magnetic ferromagnetic material. When they start lining up though, they contribute to each other and they interact more with each other. So here you can see we have a 0 net spin because we've got one spin up and one spin down. They're the 2 possible directions, and this spin lines up when we put our substance, person, whatever we're scanning, in a magnetic resonance imaging machine. Okay. Here we can see for phosphorus, sorry, we'll just get rid of that. Phosphorus 31. We have an odd number. Well, it's actually, its number of protons is 15 plus 16 neutrons, which gives us the 31 total nuclear particles. Okay, total particles, total protons in the nucleus. This is an odd number, so there's going to be one spin left over. Could be plus a half or minus a half, but it's a net spin. The number of neutrons is 16. They're going to balance out and cancel each other's spin or magnetic properties. So the norths and souths will line up and we'll end up cancelling each other out. If you think about a bar magnet, say, and you put a south and a north near each other, you can see they pretty much cancel each other out pretty quickly. Out of north into south, north out and south in, sin, remember? And because we've got this odd number of nuclear particles or nuclides, and because phosphorus is commonly part of bone and quite a lot of it in the human body, it can be used. It's in relatively large amounts. The main one that's used in MRI scanning, and MRI scanning needs to have a net spin, okay? We need that nuclei or nuclear particle, the leftover one, so if there's 1, 2, 3, these two cancel, and this one's left. We need that for MRI to work, and we'll see that over in a few videos time. MRI needs substances with a net spin. Hydrogen, again, if we look at it, has one proton. There's no other proton, there's no other neutron to interact, so it has a net spin. It reacts and is used very well with MRI scanning. It's also very common in the body. If we're 75 or so percent H2O, we've got a massive source of protons there in our hydrogen atoms. Oxygen, 816. Okay, even numbers, so oxygen's not going to be any good for our MRI scanning. Protons, however, hydrogen with its lone proton, we get that spin effect, and we're making use of that lone spin with no cancellation in MRI scanning.